Hello, I'm going to demonstrate how the RMC 75 and 150 can do a flying shear application very easily with very little programming. What you see in front of you is a graph of the motion profile for a flying shear, and I'm going to explain the lines. The bottom left-hand side is the legend, and the lines are all color-coded. So for instance, the red line is the actual position, and axis 0 is the slave or the shear, and axis 2 is the master or the reference that is monitoring the line speed. So the black line, the reference target velocity, is at 10 inches a second, and we can see the actual velocity of the shear goes from 10 inches a second when it's in sync, then it has to back up, and then it goes back positive up to 10 inches a second, then slows down. This is the reference position, and what we're doing is we're getting the shear in sync with the reference position. There's a position that's calculated called the master sync position and the slave sync position, and they get synced together at this point. And then at that point, we're at constant velocity. You can see the acceleration is 0 here, and the velocity is 10 inches a second. I can move my cursor back and forth. I can see the values change over here. And after 4/10 of a second, which is the cut time, the shear starts to retract. It starts to go negative. The acceleration is negative. And you can see the slave position backs up, goes negative, and then gets back in sync with the target or the master in the next cycle. The green line is the control signal. So let me just show you what this looks like when it's running. This is what we call snapshot mode. And what it's doing is it's gathering the information in real time, but this is a snapshot, just a 2-second graph. We also have the capability of doing trends. And if I do a trend, you can see that it's moving it moves continuously. Now, I have a variable table or the variable table monitor, and I can change the line velocity and the material cut length on the fly. And what I'm going to do is change the line velocity. Right now the line velocity is 10 inches a second. If I move the line velocity to 20 inches a second, I'm going to download it now. Now watch the black line. It's going to start to increase. Now I'm going to stop this for a second. This was very fortuitous in that, or it looks fortuitous, but in that it made the change in between the synchronization times. But I will show you that doesn't really make any difference. I'm going to slow it down back to 10 inches a second. Still made the change in between. Let's go back up to 20. This is what I wanted to show you. You can see that as the master line speed increases, the slave line speed is increasing also with it. So it stays in sync. So you can see the master's position, the angle changes at this point. And also the slave acceleration and all the other parameters must change along with it. The control output must get higher also. The program for this is very simple. It's only 3 steps. What I'm going to do is move my cursor back up and go to the program. So I'm going to expand this, go to user programs, and go to the shear sync program. And there are 3 steps. And you can see this is step 0. This is the initialization step. This is the part that does the synchronizing. And the second step just does a delay. It turns on a output, which you can see is turning on here and off. That's telling the shear to go down, and then when it goes off, I'm telling it to go back up, and I'm telling the cut to go off at this point. This is a output on the motion controller. So the cut time is at this time it's just a delay, and I'm delaying for 4/10 of a second. And that's supposed to be how long it takes the shear to go down and come back up. However, in reality, we would probably have to tell it to go down, wait for it to go down, and then have another step where we tell it to go back up and then wait for it to go back up before we go back to the sync loop. So a real program would probably have one extra step. It would be a step 3 in addition to the step 2. The key to this program is step 1. And what it does is it calculates out a slave sync and a master sync position. And it uses the advanced gear move. Now the reason why it calculates a slave sync position and master sync position, and in this case they're both the same position, is that it wants to do the cut in the middle of the stroke if possible. And if not, then what it's got to do is it tries to center it as much as possible so it has the same amount of acceleration and deceleration. And that way I don't have a lot of acceleration on one side trying to get back and a long, slow deceleration going forward, or vice versa. This minimizes the magnitude of the acceleration or the deceleration. So this is where I'm doing the calculations for the master sync position, and this is how the gear move works. You specify a sync position for the slave, a gear ratio, which is going to be 1:1, a gear ratio rate, which is going to be 0 because you're not going to be accelerating during this time, at least not relative to the master. We have to specify a master target register, and that's the target position. So we're geared to the target position. And then this is the position at which the master's sync position and the slave sync position well, that's the point at which they'll both be in sync at the same time. Then we have to specify the direction the master is going, and we have to say positive because the master is a rotational indicator. It goes forward, resets, and comes back. So sometimes it's going to a position that seems less than, but is actually ahead rotationally. So we have to specify that the direction is positive. The slave just goes back and forth, so that is assumed to be just going the nearest. The link condition is the condition that must be met before going off the next step. And what we're doing is we're waiting for the target generator to be done. And once it's done, the bit is set, and it will stay set until we give it another command. So it should be set during the whole time that the slave is synchronized to the master. And then as soon as the cut is done, a new command will be given. The target generator done bit will go off until it gets back in sync again. Then it'll go on, and this loop just continues around. So if I want to show the whole program at once, I can turn off the comments. And this is step 0, step 1, and step 2. And the only thing that step 1 does is that it waits for the master to get to the start position before it executes this slave, this advanced gear move. So you can also see that the current state is indicated by the red dot. It's kind of hard for me to chase this. And this is the I/O monitor. You can see the output for the shear going on and off. The I/O table is defined here. I've only got 2 bits. I've got a run bit defined, which I'm not really using. And I've got an output defined, which is turning on and off or lowering and raising the shear. The variables are defined in the variable table, and there aren't very many variables to this. I've got a master velocity and a cut length, and those are parameters that you change on the fly. The cut time is usually going to be, well, it's fixed in this application, but usually there isn't a cut time. There's usually a weight or an input that indicates the shear is down and the shear is up. The slave start position is close to the negative limit. And the reason why we want to be there is we want to have use as much stroke as we can out of the actuator. Then we have the slave sync position, the master sync position, and the master start position. This is the old velocity. The old velocity and the is used to change the speed. This is the master reference program. Now normally this master reference program would not be necessary because the line is controlled by a VFD and it's external. The shear system doesn't control it, it just synchronizes to it, but in this case we're controlling it. And what I'm doing is I'm setting the master velocity to the old velocity and the cut length to the position unwind. Then I change the velocity to whatever it needs to be, and then I wait for one of these two variables to change, and then I go around and I update the master velocity again. So this program is very, very simple. It just goes in a loop. So let's go back to the graph. So here we have the graph, and you can see that we change the velocities on the fly. I'm going to change the cut length on the fly just so you can see how that happens. So I'm going to move this down and turn on the plot. So now we're moving in trend mode again. So now we're going, okay, now I can change the cut length, and there it goes. Now the cut length was 20 inches here, now it's going from 0 to 30 inches up here, and you can see that it had to accelerate quite a bit to catch up, but it's still a smooth motion. Now I'm going to move the cut length back down to 20. You can see that it moved down. Now the reason why the scaling didn't change is because it's still going to remember the 30. And I can also change the speed on the fly. Let's change two things on the fly. Let's change the speed to 25 and the cut length to 30. So you can see that it ramped up nicely and the speed, the cut length changed to 30. Another cool feature that we have with the RMC is the event log. What I'm going to do is call that and move that up here. Now there isn't much to see on this one, except for the fact that what we're doing is we can log every command that's issued to the RMC, and you can see that we're only issuing one command. It's called the advanced gear move. But one of the cool things is that we can see the calculations that are done. We can see the output being changed to false, and up here it was changed to true. And we can see when there's a transition in the task to step 2, and we can see the intermediate calculations. For instance, the master sync position was set to 7, and the slave sync position was set to 7 inches. So we can see all the intermediate calculations in all the times. So this makes it very easy to debug your program. But a program like this doesn't take too long to debug. That concludes my demonstration. Thank you.